We are happy to have with us Mr. Anoop G. Prabhu. He is the co-founder and Chief Technology Officer, Vehant Technologies. He is responsible for aligning the company's technical competence with the emerging trends and futuristic technologies. He was also the co-founder of the company's Critical Solutions and Critical Secure Scan. He holds BTech and MTech degree in Computer Science Engineering from Indian Institute of Technology, Delhi. We are happy to welcome you, Mr. Anoop.
Thank you very much, Dr. Indu, for the kind introduction. So I would request if my audio and video are clear. Could you just confirm?
Yes, we can hear you, but the screen is not. You are not presenting the screen.
Yeah, I'm just doing that.
Yes, now we can see your screen also.
Right. So, is the screen visible?
Yes, it is visible. You can start.
So, so Indu had already given a brief, but just to elaborate a little bit on that. So we were started as a company founded from IIT Delhi with the founding team comprising alumni and faculty in 2005. Earlier known as Critical Secure Scan, we were initially part of the Critical Group. And over the period of time, we have worked on multiple products in the areas of traffic monitoring and security-related systems. Presently, so we have a global footprint spanning across multiple continents, and we have 7 offices, including multiple in India, Indonesia, and Netherlands. Over the last so many years, we have worked on multiple technologies, including computer vision, machine learning, deep learning, and X-ray, thermal imaging, and video and image processing being some of the key technologies that that we have used to power the products that we have. The business segments that we focus upon have been so traffic enforcement has been one major segment that we are focusing upon currently. Also, traffic monitoring, which includes monitoring of non-enforcement related traffic, and as well as solutions for people monitoring, including things like AI-based mask detection, social distancing, etc. So I'll just come directly to the problem at hand, which is more relevant for this workshop. There are some unique challenges for the Indian traffic concern. There are a plethora of problems that are present, and as you can see on the screen, there are close to 300 million vehicles, and the one significant problem is because of the unorganized, non-lane-based driving employed by a lot of drivers in India. The second major problem, which is more of a technology and infrastructure problem, is the large heterogeneous mix of different types of vehicles in India. And one of the major concerns as a result of all of this is that the number of fatalities in India is significantly high compared to many other countries on a per capita basis. So, and significant among them are deaths of two-wheeler drivers and passengers, and so due to the fact that they are more vulnerable on the road. And however, whereas technology has enabled solutions for many problems, including detection and enforcement, India being a very value and price sensitive market, the solutions have to deliver much more value in the same economical footprint. So this is a typical lane discipline scenario of traffic in in certain countries compared to the Indian traffic scenario that we have on the right here. I mean, so this is not an India-specific problem. There are probably a lot of other countries who have such unorganized and heterogeneous mix of traffic. The Indian tendency of the Indian driver is to maximize the use of the road space to the extent possible, which results in also significant vehicle congestion and much lower speeds, especially in heavy city traffic. In order to monitor and help the authorities manage the traffic, we have certain solutions which have been used widely across India. So as we speak, so more than close to 25, 30 cities in India have deployed our solutions for traffic monitoring, including for red light detection, speed detection, as well as of recent some of the analytics powered by AI, especially including detection of no helmet and triple riding, vehicle make and model. So the one of the key components of all of these is that all of these are camera driven primarily detections, and there is no other sensor component as opposed to typical solutions which are deployed in the Western countries mostly. So the unique advantage that this offers is also partly because of the nature of the traffic solution, I mean, the nature of the traffic that we have in India. So I will jump right into explaining two use cases that we have tried to solve in a uniquely Indian way, so to say, and so hopefully it will enable some of you to look at more challenges in the Indian traffic space. So when we talk about structured versus unstructured traffic, it is significant not only from the uh, context of the autonomous driving scenario, which is how it has been traditionally been looked upon when we talk of unstructured traffic and unstructured environments. But it's also important from an infrastructure perspective of the ITS system implemented also, in the sense that all the systems that are implemented for the traffic solutions at the junctions, intersections, as well as on the highways, should also be able to work with the same kind of traffic scenarios that are present. So in order to focus uh, the system to be able to handle these scenarios, so we have come up with certain unique ways to tackle the problem. Uh, Whereas somebody from a typical a researcher from a typical standpoint may look at the problem as just as a detection and then a classification problem, wherein we can run a neural network on the video and then do all detections and then eventually flag any violations, etc. as a due course. So we have looked at the problem in a slightly different way, owing to the fact that most of these solutions are deployed at the edge, where where the amount of compute is not uh, very huge. So GPU compute, even if it is available, is not of a very large order of magnitude, and therefore, and it sort of was built on top of our existing pipeline of ANPR and traffic violation detection for red light and speed. So we look at the number plate as a unique identifier, and then use that in order to detect violations of the helmet and triple riding uh, violators. And so why this helps significantly is, let's say we talk of a scenario like this, wherein we have a 3-lane or a 4-lane road, which is congested with or clustered with a lot of uh, vehicles standing together, then directly running a model to do a detection of the number of vehicles and the people and flag all the violations here would also run into problems of scenarios wherein the model is detecting pedestrians as well as people on bicycles, etc. All of which, from a traffic enforcement perspective, is actually meaningless. Because plus, even if, let's say, we end up detecting this algorithm detects as a system. or a violation which of a person on a bike without a number plate, then no potential action can be taken on that, even if that is a correct detection. So therefore, in order to do any sort of further action, the number plate is sort of a preliminary as far as the traffic authorities are concerned. So this probably can give you a sense of the kind of unorganized traffic scenario that the system has to cope up with. And so with some of the potential violations from this particular viewpoint have been highlighted in red and the non-violations in green. I'll just explain the pipeline and how we have looked at it. So as I mentioned, so we drive the control flow from the APR system. Initially, it started as an intern project to do a very simple and quick POC proof of concept. So therefore, we did not do anything fancy when we started. So all that we did was that we took an ROI around a certain region over the number plate region. So based on the location of the license plate, we chose an ROI around about it, where the location of the rider and the pillion would be there, and we put in a very basic classifier. I think it was an AlexNet, and which is and took pre-trained weights and just fine-tuned the last few layers, because we didn't have too much data also, or rather the intern did not have too much data to start with, and we were able to do a very quick POC demo with it. And yeah, so this is sort of the basic pipeline. So look at a vehicle, extract the number plate, use it to figure out a suitable ROI about it, and do a very basic classification. So these are two sample scenarios, and surprisingly, it did not do all that bad. It was, in fact, it was able to do reasonably well in these kinds of conditions, very accurately. So all of these were, could be very easily detected as people wearing helmets, and similarly, all these vehicles were were detected accurately as people not wearing helmets. Just by just simply doing the basic classifier. Going ahead, we were also able to tune the system by adding some more data to also work for double riders as well, as in vehicles with two riders also. So such kind of scenarios were, as shown on the screen, were also handled reasonably okay without too much of errors. But of course, when it comes to cases where some of the more complex cases, then the system sort of it failed rather well, I would say, to put it in context. And of course, the triple riding instance on a bike, then it sort of would never really handle it in any possible way. So basically, as long as the orientation and the location of the head regions were more or less uh, within the same limits as the training data that we had, then the very basic pipeline could do it rather well. So yeah, so now then we did a pipeline change, and we have the control flow being driven by the NPR. But now instead of putting a classifier as a base, so we started by putting a YOLO-like detector on a slightly larger region uh, around the vehicle over the license plate, and then we use the ROI region for detection and run a classifier on all the different heads that are detected in that particular region. So what we get is that we have an ROI like this about the license plate, and then so we run YOLO on this image, and or a YOLO-like classifier, because all of this is running at the edge on a reasonably low compute. I would say, compared to the kind of AI networks that are needed to get good accuracies. So we sort of took the basic YOLO architecture, sort of stripped it down to the very basic minimum that is needed, and of the multiple detections that we get in this region, then we run a very lightweight classifier to say whether it's a helmet or not, no helmet. So now suddenly, even if there are two people, three people at different orientations of the heads, all of that could be detected very well. and we could then classify that it's a helmet or a no helmet, even when there are multiple people. So helmet, no helmet, and triple riding detection was done rather easily with this. Yeah, okay, I wouldn't say easily, but this pipeline is able to handle that in a reasonable and easy manner. Some more examples of similar kind of scenarios. The system works reasonably well both at day and night, and has been running really well across multiple cities now. However, of course, there are still many challenges to be resolved. So some of them being images of the kind that we see here. So so there are some cases where we have misses, especially when people are sitting reasonably close to each other. Sometimes there are misses happening. There are misses as in the middle image here, wherein one head is reasonably the head of the middle person in the middle is reasonably rather well occluded by this person sitting behind. Sometimes false detections on turbans, especially similar to the kind that we see on the right here, and sometimes on shadows as well. Though of late, some of our team members have been working on removing many of these false alerts. Yeah, but still the problem sort of is far from being completely resolved. So going ahead, we have also looked at segmentation-based approaches to see whether that can help us solve the problem. Of course, they are computationally rather expensive, and we have to look at the computational burden before being able to deploy it at the edge. Yeah, but in the realm of research, I would think that something along the lines of segmentation or would definitely help us do better than what we are doing currently. And of course, we would welcome suggestions from all the researchers here and the research community to point us in a better direction to solve these open problems that we have here. Okay, I'll move to the. Okay, before moving, so eventually the screenshot that we see here, this is similar to what how the final result is presented to the end user with a zoomed in image of the vehicle, wherein the number plate can be seen very clearly. Of course, the number plate has already been detected and read, and that is also available. But along with that, multiple overview images are also available in order for the user to make a better judgment on the type of violation that has happened. Okay, I'll now quickly move on to the second use case that we want to discuss today, which is the vehicle detection scenario in the Indian context. So TrafScan is a product for vehicle detection, and it's essentially a camera-based vehicle detector meant for help in intersection signaling to help the automated traffic system there make better decisions about the time of the traffic signal and how to interconnect different signals together in terms of maybe allowing green corridors, etc. So, and in order to improve the overall traffic throughput. So the system, has a so this is this is a schematic image of a sample trap scan view, and how it can be configured with multiple zones, typically one or two zones per lane. Uh, so this system provides input for both for vehicle actuated traffic signaling and its larger cousin, the ATCS systems. Uh, Configuration is zone based, and typically the system provides occupancy count and classification, average speed, flow of vehicles, statistical inputs on vehicle density, queue length, etc. Of which occupancy is primarily the most important for the local traffic actuation. The other inputs are used by some of the systems that we have integrated with, and in some cases, so even reasonable accuracy of the count or classification, etc., also helps the city planners make much better improvements in the overall traffic management. So initially started as a as a replacement for the loop detector, which was used earlier in order to do traffic sensing. It runs on a on a rather low power, low compute hardware platform, uh, and the system flow basically, because of the low power, low compute, it's essentially just very simple motion based detection, and using a basic motion model with some filters on top of it to remove false positive, handle clutter in some very basic manner, etc. And classification based on size on the vehicle size. I'll just show a sample video here for continuing with the rest of the presentation. I hope the video is visible.
Yes.
Dr. Anoop, yeah, please. So as you can see, so this is a very simple background model. It can detect based on very simple frame differentiating motion, and very lightweight. It is able to create a mask, foreground mask of the objects, and just based on the size of the object, very simple size based classes can be done. But of course, so we have only 3 4 classes here based on the size. It's very difficult. It's difficult to go more granular than that. As you can see, the person is also detected. The person on the right, when they walk, as long as they are not in the field of view of multiple vehicles clustered together. Yeah, but very soon, once the okay, so that was a very basic system to get an idea. I'll come back to the presentation. So it was a very basic background model, which is lightweight, and being a very basic motion model, so there are issues with clutter, and it is able to handle only very few classes based on size. But of course, this serves the need of of the wide of a large variety of ATCS and traffic signaling systems that are currently used in the country as well as even globally. So far, across all the systems that we have looked at and are interacting with even globally, so there are only few which actually make use of the wide variety of information that can actually be provided through a computer vision and AI based pathway. Yeah, but nevertheless, so we are looking at how we can improve things going ahead. So we are so obviously for the next step to look at to consider, once very basic things don't work, is to look at a DL based approach. So where we have trained a detector based on Indian data, owing to the number of heterogeneous classes like auto rickshaw, e-rickshaw, etc., which are not really, which are sort of India specific, or the subcontinent specific, more to say, India and similar India like countries. And but the problem being that the TL model will be high compute intensive, and so would either require a reasonably medium end GPU or a top end CPU in order to run it for one camera. And typically at a junction we have 4 cameras. So that would mean that reasonable compute infrastructure needed at the junction in order to be able to run this. So we did a mixed architecture wherein we run the background model for the detection and count, and we use the DL network only every n frames or so, which is configurable, but typically it could be like every 5 frames or every 10 frames. Again, it's sort of it's dynamic based on the uh, velocity of the whole traffic flow at that point, and you use that to improve the classification result only. So this share a sample here. So yeah, so this is roughly pretty much the same chain, but we can now handle auto rickshaw. So we have classes like auto rickshaw, e-rickshaw, etc. also being detected here, and that is, for example, now gets detected as an e-rickshaw. Okay, as you are seeing these videos, there is a lot of flicker happening because this was probably done, as in the video was generated by running the YOLO every maybe third frame or fourth frame, and this is not exactly the final output that goes to the end user. But yeah, this is only for visualization, and which is why we're also seeing certain stop and certain other annotations around the video. But yeah, but broadly by and large, it works reasonably well. And so this is not the full YOLO model that we are running here, as I said earlier also. So because of the compute requirements, we are running a much more lightweight version, uh, even lightweight than time YOLOs in a certain sense. Okay. So now with this, so what we are able to achieve is that we have good accuracy on detection. So even earlier the accuracy was good, but now we can do slightly better, especially in scenarios where we have clutter, etc. So some improvement in the overall count of vehicles at a statistical level. Definitely improved classification in terms of now we can have classes like auto rickshaw, e-rickshaw, etc. also in the pipeline. Going ahead, even more classes are being planned to be added, but they may not, but we may or may not do it depending on the requirement. From a theoretical and a research perspective, that's a very straightforward done. That we can go up to 10 or 12 or 15 classes reasonably well, but just by adding more training data, and possibly we may need to increase the computational burden of the at the edge, or we may need to maybe run it at the at the central cloud server in order to be able to process that. Yeah, so as you can see here, there are some snapshots of the system detecting an e-rickshaw. So cycle rickshaw and e-rickshaw both have the same class, and the auto rickshaw here on the right. Okay, so now the system works well, but so what's now the problem? The problem is that the significant part of India has foggy weather for at least 2 months in a year, and visibility in foggy weather conditions is definitely an issue for the visible camera. And these are some sample snapshots, right here from NCR. As you can see, it is reasonably hazy, and this is not heavy fog; it is just mild fog. So, okay. So what are the issues? Is that accuracy, the detection, and the classification drops. So occupancy and signaling continues reasonably well. So as far as the traffic signaling at the junction is concerned, so that goes on reasonably well without any issues. So while the system performance degrades, it does so reasonably in a robust manner. However, the larger, more value-added information like queue length and statistical information about distribution of traffic across different classes, etc., all of that suffer drastically, in the presence of fog. So we've looked at some options of handling fog, like fog and haze removal algorithms, which on one side is computationally intensive and not really feasible to run at the edge. But yeah, from a research perspective and as an internal project, we've tried it, and with only very slight improvement in results. So before going, so I'll show a video just to show an idea of what kind of results are possible. So this is a sample video of after doing some amount of correction for the fog. So as you can see, the now there are more vehicles in the scene. So as vehicles come in, so the background model has sort of become slightly better after doing the haze removal and some filtering, but still there are issues, especially when there's clutter and overall, it's not really worth the computational overhead of doing haze removal and still not get really good performance after doing all of that. So it improves slightly, but not drastically, and does not give the desired output. As you can see, there are false trails left behind because of the visibility issue. So what next? So thermal camera seems to be the option that we can easily look at as a next step, wherein it provides improved visibility at night, even with no lighting, which currently, in most cases, the existing visible camera also does it because it's infrared sensitive, and infrared illuminators are usually installed at the intersection along with our other cameras. However, fog is one issue where infrared, while it helps slightly and works okay for in-car systems, it still does not help for a very wide-angle view. So that is where thermal actually really shines. And so this, for example, is a sample thermal output of the camera. And of course, so now we come to the problem of how do we, and because this video stream is completely different from the visible stream, how can we, so do we have to do the annotations all over again in order to be able to make use of the advantages of deep learning? So no, so that would be having very heavy cumbersome activity. So we're looking at an option, or we have explored options of aligning a visual camera and a thermal camera together, and try to do sort of semi self supervision from the detections of the visual stream, and using that, then and train a model on the thermal video using that. So that seems to be doing reasonably well. And of course, there are other options also to look at cross domain adaptations, but we haven't really seen in our initial experiments, we haven't seen them do all that well, especially in going from the visible domain to the thermal. Probably it could be because of the traffic specific scenario. So this is the visible stream and the detection that we have here, and so we transfer the same to an aligned. So as you can see, it's more or less aligned. Field of view is slightly different, but it's reasonably aligned, and but it's not 100% perfect because the two cameras, I mean, because these are not machine vision cameras, and there is no synchronization at a frame level. But as long as the vehicles don't move really very fast, and the intersection that we're looking at, the transfer is reasonably okay, and with very little manual overhead, where if there are gross errors, that correction has been done, and so with very little fine tuning on the manual side, so we can, by parallel, we can get a very good model to work on the thermal video. So let me just show that, and that sort of brings me to the end of the two use cases that I was talking about. I'll just take a few more minutes, Indu, if I may, before closing this, to motivate people on some more open problems that are available. Okay, so is the video visible now? Or?
Yes, it is visible. Yes, it is visible.
I'll just skip the first few seconds that was being played earlier. So this currently is the mixed model running, as in back motion based plus thermal being driven by YOLO. So with that, I'm fairly done with the use cases. I would just like to spend a few minutes to speak of some open problems which we are currently looking at. So we have looked at two use cases from unstructured environments, and as we've seen, there are many open research problems in this domain, and the Indian traffic scenario in general has a plethora of research problems waiting for a researcher to grab it. I will show one more example of that, or one or two examples of that before getting into it. Yeah, so it's 25 seconds. This is video from a junction from where we have some of our cameras installed, and I've just so now this is, you could say, maybe a typical Indian junction. So if you notice, so you can see the bike that went from here to avoid the traffic light, it circles around from there, which we are seeing here, and then it goes out from there. In the process, also avoiding a near hit, etc. But this is a very common problem that we are seeing in the Indian scenario, and especially at very crowded junctions, etc. So so this is a problem which, from a vision perspective or an AI perspective, is very easily detectable and solvable. Of course, it will require some amount of probably researchers and the industry may be coming together for data and research initiatives together in order to be able to solve this problem maybe. But that is definitely one area where some things can be done. A second instance, also in the same video, if you notice, we'll just see what time instant it comes. About 2 minutes. Here are 2 minutes. Almost there. So, yeah, so as you can see, there's another vehicle here which is coming from the wrong side. Yeah, so near 2 minutes, when the phase of one traffic one approach ends and the next one starts, so that interchange phase. Yeah, so this at this point, there's a lot of near misses happen at this point, and this is something that we've seen across multiple intersections at different locations. It varies from city to city depending upon how strong the police enforcement is. However, in no city is it completely zero, and definitely so the interaction between vehicular traffic as well as pedestrians and non-vehicular traffic is something non-motorized traffic is something definitely that is of interest to study, both for researchers as well as for the from a planning perspective for the traffic planners in order to be able to better manage the traffic infrastructure. Uh, so with these, I'll stop my presentation for today and take questions if there are any. And yeah, so customary notes. So we have research positions open at Vehant, the area of not just in traffic, but also in security, X-ray, and AI in general. And if any of you are interested in looking at in doing some good research, please do contact me at anoop@vehant.com. Thank you everyone for keeping up with me at this time of the night if you're from India, and yeah, a good day ahead for the rest of you.